All right. Good afternoon, everybody. Thank you for coming to Lecture 7 of the Intro to Space Navigation class, Spring 2025 edition. Appreciate you putting up with any schedule changes and technical difficulties that come along with me presenting from my conference hotel room. I'm also not presenting from my normal desktop computer. I tried to download all the right software onto my laptop, and so things will be suboptimal today, but I think we can get through everything just fine. So let's talk more about orbit determination. So let's see here. Trying to remember if last time I called it initial orbit determination or just orbit determination. I'm going to call it orbit determination today. Orbit. Okay, I have to get used to a new, hang on. Sorry, I like my font size to be a little bit larger here. There we go. Orbit determination. Part 2. So, I'll underline this. So last time, we introduced the whole problem of orbit determination, and then we focused on Gibbs' method, you remember, which is 3 positions. And then also Lambert's problem. Oh, 1 second here. There we go. And Lambert is 2 positions as well as delta t between them, right? So the idea, oh, this should say Lambert, not Larnbert. There we go. The idea behind orbit determination in general is estimating your full state from a whole bunch of partial states, right? So if you have your position, that's great, but what's your velocity? Well, if you have 3 positions, you can fit an orbit ellipse to them following kind of the 2-body laws of motion, and then deduce your velocity corresponding to any one of the positions. And we remember from a couple of lectures ago, if you have your position and your velocity, that's the same thing as having your orbit elements, right? It's just a simple mathematical conversion from one to the other. Similarly, there's enough information in 2 positions with the time of flight between them, and that's Lambert's problem. So today, we're going to be talking about, it's going to look like a lot, but you'll see it's not quite so bad. We're going to talk about Gauss's method, which is what's called angles only. We'll have a very brief description of Gooding's method. And there's also the what I'm calling the Christian Hollenberg method. So we're going to do very brief description of Gooding. We're going to go into gory detail on this one, and then I'll just say and more. Okay. Now, I will say, and I hesitate to say things like this, none of today's lecture is on any of your homework assignments. So there's going to be a temptation to just kind of phase out, be like, okay, neat, thanks, professor, which you can do if you want to. As a reminder, though, we're expected to do a final project in this class, which involves kind of going and learning something tangential to what we went over in class and kind of saying, oh, I thought, lecture so-and-so was really interesting. I want to go do more about that and go find some paper or some article to read. So some of you might decide that you want to code up a simulation of different orbit determination techniques as your final project. And if that's you, then this lecture is just pure gold. So I encourage you to pay attention. So let's talk about Gauss's method. Any questions before we dive in further? Neat. All right, so the guy's name is Carl Friedrich Gauss. He lived from 1777 to 1855. And he used the method we're about to learn to find the orbit of Ceres in 1801. So really quick, does anybody know what Ceres is?
the largest asteroid and was briefly considered a planet.
Yep, exactly. And by that same token, I don't know if it was the first or one of the first asteroids that anybody ever actually saw, because it's so large. But yeah, it's large enough to be roughly spherical under its own gravitational effects. And I think it's bigger than some moons of some planets. And it's definitely bigger than Pluto. So
It,
yep,
it
that's
um it was the first asteroid found. It isn't bigger than Pluto. I think its radius is about 500 kilometers, and Pluto's about like 1,500.
is it? I thought for sure it was bigger.
It's
Okay.
it's teetering right on the edge of hydrostatic
Okay.
equilibrium. Definitely
Oh,
bigger
okay.
than like Mimas and such.
Got it. All right. Well, thank you for the update on that. Appreciate it. So the idea then is Gauss used this method to determine the orbit of Ceres. Now, the most readily available measurements of spacecraft, asteroids, etc., are optical line of sight measurements. We'll abbreviate that as LOS. So this would be something that you get, for example, from a telescope or camera. So we kind of glossed over this before, but with Gibbs' method, we get 3 positions, and then we turn that into a velocity, or we get 2 positions and a delta t in Lambert's problem. But finding a position is a whole lot more difficult than you might think. It's a lot easier to take angular measurements, so azimuth and elevation, or right ascension, declination, take angular measurements to a body with a telescope, and then wait a little bit and take those again, and then wait a little bit and take those again. So we need an orbit determination method that only uses angles. And you might be shocked to find that initial orbit determination using only line of sight measurements is called angles only IOD. Sometimes you'll hear this called bearing only IOD. Same idea. And this is really where the meat is, because most orbit determination problems, you only have these line of sight measurements. So let's do a quick diagram here. And let's say, here's the Earth. I'm going to try slightly harder to make that a circle. Kind of a lateral move. And let's say that there's some ground station right here. Now, this is meant to be on the surface of the Earth, not inside the Earth, right? And let's say that then there is some spacecraft out here, and you've got a line of sight like this. And that is at some time t1. Then at some time t2, the spacecraft is here. But the ground station also moves, right? Because the Earth is rotating. So at some future time, looks like this. And then at some still distant further time, it's over here, and your ground station's over here. Right? You've got a ground station motion because of the Earth's rotation. You've got the orbital motion of the body, which looks like this. I'll try to kind of, there we go. And we're going to call this measurement U1, U2, U3. And we're going to call this distance rho 1, rho 2, rho 3. And to kind of make this make a little bit more sense here, let's just look at one of these measurements. Here's our ground station. I'm going to say that the vector from the center of the Earth, the origin, to the ground station is some capital R(I). And I'm going to say that the vector out to the spacecraft is some lowercase r(I). And I'm going to say that the line of sight direction, which points to the spacecraft, is ui, and then the distance is rho(I). So that builds up this equation, which might be kind of natural from what we see here. The vector from the center of the Earth to the observer plus some other vector, which is the line of sight direction scaled by some unknown range. Well, that's equal to the spacecraft position. So this is observer, and this is known. This is range, which is unknown. This is your line of sight, which is measured. And this is the targets, which is also unknown. So what is our problem? The problem is given, we're going to say Ri and Ui and a time where I equals 1 to 3. Find R2 and V2. Because remember, if you have your corresponding position and velocity, that is your full state, that is your orbit elements as well. Okay. Questions about the Gauss's method setup? Okay, so moving on. Also, it might be clear here, each measurement gives us 2 pieces of info. You could think of like azimuth and elevation. But the full state is 6 degrees of freedom. So therefore, we need at least 3 measurements to solve this problem. It's always good to stop and think about like, okay, when do I have enough information to actually try to solve this? And when am I just kind of kidding myself, right? Okay, so I'm going to move this briefly here. All right, so let's get into the math. Recall the coplanar constraint. From the Gibbs derivation. So that was this, right? The second position must be some linear combination of the first position and the third position, where C1 and C3 are unknown, but those are in theory things we can solve for. Okay. We can also use the Lagrange coefficients, which are from the Lambert's problem lecture. So that would be R1 could be expressed as some linear combination of R2 and V2. And similarly, R3, you should be able to express that as some linear combination of R2 and V2. So now we've got these coefficients, F1, G1, F3, G3. But you can see how we should be able to plug this into this, right? We can see where this is going from here. If you combine this measurement equation, capital Ri plus rho I ui equals little ri, and you combine that with the coplanar constraint, and you combine that with the Lagrange coefficients, all of these are models of either the measurements or the dynamics going on underneath the physics that we're seeing. combining our equations, we'll say combining our models, gives us 18 equations, 18 scalar equations, and 18 unknowns. I'll spare going through and counting them, but if you wanted to, you can convince yourself that this is actually a solvable problem. Okay? We'll begin by finding the Gibbs coefficients, C1 and C3, in terms of the Lagrange coefficients. So we're just combining these equations together, if that makes sense. And if we do that, we get C1 is equal to G3 over F1 G3 minus F3 G1, and we also get C3 is negative G1 over F1 G3 minus F3 G1. Now, we make an important assumption here before we move on. An important assumption that the time between measurements is small. So whenever you see things like this, your brain should probably jump to linearization, right? We're about to linearize, we're about to drop higher order terms, so we need to assume that delta t is small. And that is exactly where we're going. We also define time intervals tau 1 is t1 minus t2. Tau 3 is t3 minus t2, so time since the second state. And then tau is just the total gap, t3 minus t1. All right, now I'm going to skip the derivation and just give you this. The Lagrange coefficients are to first order. So you can compute Lagrange coefficients as functions of time and then just drop the higher order terms. We get that F1 is approximately equal to 1 minus 1/2 mu over R2 cubed. So this is the scalar R2, tau 1 squared. And then F3 is approximately equal to 1 minus 1/2 mu over R2 cubed, tau 3 squared. G1 is approximately equal to tau 1 minus 1/6 mu over R2 cubed, tau 1 squared. And G3 is approximately equal to tau 3 minus 1/6 mu over R2 cubed, tau 3 squared. So as ugly as this looks, we skipped a lot of even uglier steps to get here. Right. Now remember, what are we trying to accomplish here? We're trying to find equations that relate these positions to one another here so that we can solve for R2 and V2, right? Now it looks like R2 and V2 are functions of these. Sorry, I'm getting myself all twisted up here. R2 and V2 are related to R1 and R3 by these Lagrange coefficients, but R1 and R3 are related to R2 by these Gibbs coefficients. And now the Lagrange coefficients are functions of the delta t's and then also the scalar R2 value. So we can kind of combine like terms here. This allows us to approximate the Gibbs coefficients as functions of time. So that would be C1 is approximately equal to tau 3 over tau, 1 plus 1/6 mu over R2 cubed, tau squared minus tau 3 squared. And then C3 is approximately equal to negative tau 1 over tau, and then in parentheses 1 minus 1/6 mu over R2 cubed, tau squared minus tau 1 squared. All right, so we're not quite done yet. Next, what we want to do is find the unknown ranges, right? If we knew rho 1, so we'll go back up to this equation here. If we knew rho 1, rho 2, and rho 3, we could find R1, R2, and R3, and then it's Gibbs equations after that, right? So finding the ranges is really what we're after here. Okay? But then how do we do that? So I'm going to drop another couple of equations in your lap without derivation for now, but through linear combination of the measurements, we can deduce what is basically a whole stack of equations here. So bear with me while I just write these all down. So next, we seek the unknown ranges. So we'll get rho 1 is 1 over d naught, I'll explain what that is, and then in parentheses, negative d11 plus 1 over c d21 minus, I'm sorry, this is c1, minus c3 over c1 d31. Similarly, rho 2 is 1 over d naught, negative c1 d12 plus d22 minus c3 d32. And then rho 3 is 1 over d naught, negative c1 over c3 d13 plus 1 over c3 d23 minus d33. Okay, where d naught is equal to u1 dotted with u2 crossed with u3. And then here come the rest of these. D11 is R1 transpose u2 cross u3. D21 is R2 transpose u2 cross u3. And then D31 is, you guessed it, R3 transpose u2 cross u3. And we've got D12 is R1 transpose u1 crossed u3. You can guess how this is going to work out. And then D13 is R1 transpose. Maybe you see the pattern here already. U1 cross U2. I'm not going to bother writing the other ones. You can kind of see the pattern at this point, right? You're welcome to go through it and complete these on your own. Just in the interest of saving time, I'm going to keep moving. So the only unknown after all this math, and I realize we've skipped some steps to get here, is the scalar R2. Let's review why, right? We have found that rho 1, rho 2, and rho 3 are combinations of these D values, which are basically just cross products and dot products of things we already know, and these Gibbs coefficients, C1 and C3, okay? But then C1 and C3 are functions of R2 and R2. So here's the scalar R2, here's the scalar R2, right? The scalar R2 appears all over the place in these equations, and it's super nonlinear. There's no way we're going to go through and like cancel them out, that sort of thing. Basically, we need to know the distance from the center of the Earth to the spacecraft corresponding to the second state, which it's kind of like, okay, we need the answer to the problem to get the answer to the problem. It's like, well, don't fret. There's actually a way to solve this. But hopefully we see if we knew the scalar R2, all the other dominoes fall down and the problem is solved. So I'm going to pause here. We're most of the way done with the Gibbs derivation. There's one last little bit that we need to talk about. But questions, or sorry, the Gauss derivation. Questions on Gauss. We've kind of reached a natural checkpoint. All right, let's solve for the scalar R2 then. So R2 vector transpose R2 vector is just capital R2 plus rho 2 U2 transpose capital R2 plus rho 2 U2. That should make sense. Now, if we take this a little bit further, we can say R2 squared, which is just if you dot a vector with itself, you get the norm squared, is equal to, and if you carry out this dot product, we'll get R2 squared, scalar, plus 2e rho 2, we'll express what e is in a minute, plus rho 2 squared, where e is defined as R2 dotted with U2. Okay, so how does that help us? Well, again, we're going to skip several steps. After much algebra, we can write an 8th order polynomial that looks like this. R2 to the 8th power plus a R2 to the 6th power plus b R2 to the 3rd power plus c equals 0, where a is equal to negative capital A squared plus 2a plus R2 squared. B is negative 2 mu, there's the gravitational parameter, b, and then in parentheses, a plus b. And then c is negative mu squared b squared, where capital A, like I said, much algebra, right? Capital A is 1 over d naught, and then in parentheses, negative d 1, 2, tau 3 over tau, plus d 2, 2, plus d 3, 2, tau 1 over tau. B is equal to 1 over 6 d naught, and then in parentheses, d 1, 2, tau 3 squared minus tau squared, tau 3 over tau, plus d 3, 2, and then in parentheses, tau squared minus tau 1 squared, tau 1 over tau. There it is. So combining all of our equations, we get capital A, which is some function of stuff that we know, capital B, which is some function of stuff that we know, and then we can compute lowercase a, lowercase b, lowercase c. While this is really ugly, we can find a, b, and c, and we can build this 8th order polynomial, and we can solve this 8th order polynomial for R2. So while this is ugly, we can build A, B, C, then solve the 8th order polynomial for R2, the scalar value. So this is where there's a couple of different paths forward. If you're familiar with polynomial solving, there's not going to be a closed form solution for R2. So typically what we'll do is solve it numerically. Now, back in the olden times, you would start with some initial guess, and then you would use some sort of Newton iteration to get there. You could also just solve this numerically. I know MATLAB has the roots command, or there's like polynomial, so on and so forth solving. We're going to skip over how you solve for R2, because that's kind of up to you. If you want to bark up this tree, solving an 8th order polynomial is pretty trivial, and we're not going to bother explaining it now. But once we have R2, we can find row 1, row 2, and row 3. Then we can find R1, R2, and R3. And at that point, you could either put that into Gibbs equation, or you could say, finally, rearranging the Lagrange coefficients from before, we would get V2 is equal to 1 over F1 G3 minus F3 G1, and then in parentheses, negative F3 R1 plus F1 R3. And that's just from the beginning of this derivation. And there we go. So we're done. Let me summarize this, because I realized this was quite a dense derivation to drink in. So thus, the Gauss procedure is compute those time values, tau 1, tau 3, and tau. Step 2, compute the 10 scalar terms. Dij, we'll call them. Remember D10, D11, all those ones. Then we compute A, B, and E. Then little a, little b, little c. And set up 8th order polynomial. Solve for R2. So there's your polynomial solution problem. Next is find the Gibbs coefficients, C1 and C3. Then we find the unknown ranges, R1, or sorry, row 1, row 2, row 3. Step 7, find positions. R1, R2, R3. Step 8 is approximate the Lagrange coefficients. F1, F3, G1, G3. Step 9 is find the velocity corresponding to the second position. And then step 10, which is optional, you can go from R2 and V2 to true anomaly 2, E, A, omega, I, and omega. And that's it. That is the Gauss procedure. So you can see how, because we're starting with less information, we're starting with line of sight directions to a target over time, we have to do quite a bit more math. And also, this math had some assumptions built into it. So let me pause, let people catch up. Can anybody remind me or point out any assumptions or shortcomings of Gauss's method?
We're assuming a very small time interval between measurements.
Exactly. But then that introduces its own problem, right? Because didn't we learn before that orbit determination problems are more observable the longer the time is between measurements? So we create this problem where if you wait a long time to let your orbiting body move a whole bunch so that you have better observability, you're actually hurting your linearization approximation here. So Gauss's procedure is going to kind of bite you either way. There's another one I can think of too. I actually glazed over this, and I'm wondering if anybody caught me just skipping something important. Where?
Are we
Let me pose
assuming
it.
the observer is stationary?
Oh, sorry, say again.
Are we assuming that the observer is stationary?
We're assuming we know the position of the observer. So in this case, it's somebody on the Earth. But I mean, capital R, this could be another spacecraft, that sort of thing. You're assuming that wherever the observer is, you know that pretty darn well. But I think that's a reasonable assumption. I'm more concerned about that big old gory eighth order polynomial. Now, in general, when you solve a parabola, it has two solutions, right? And when you solve a third order polynomial, cubic polynomial, it has three solutions. How many solutions will an eighth order polynomial have? That's not a trick question, it's 8. So if you have 8 solutions to this eighth order polynomial, which one of them is the real one? There's going to be some doppelgangers in there, right? Now, fortunately, several of your solutions will be complex conjugate pairs, right? So if you go through and actually solve for your solutions, you'll find that you'll get some number plus something I and then some number minus something I. You can get rid of those. The scalar R2 is definitely going to be a real number, and it's also going to be a positive number. So you'll get some negative solutions for R2 as well. You can discount those. But generally, there will be at least 2 somewhat reasonable solutions for R2 that we would need to work with. And so that's where you really do need a decent initial guess. You kind of have to have a rough idea of R2 to even attempt to solve this problem. So you're not going to be solving this completely from scratch, if that makes sense. Okay, so I want to move on and very quickly talk about what's called Gooding's method, and then I think we can take a little bit of a break. I'm not going to go into gory detail on Gooding's method. I just want you to be aware of it because I think this is more modern and is generally favored over Gauss's method, although the derivation is quite a bit worse than the Gauss derivation. So I thought, let's just mention it so we can say we mentioned it. So for reference, Gauss's method is from about the year 1800. Gooding's method is from the 1990s. So this is newer stuff. So we will briefly, very briefly, discuss a more modern IOD technique. Developed by R.H. Gooding in the 1990s. This is another method of IOD and is considered the gold standard today. And this is the exact same problem set up as Gauss. So this is just, is there some other way to get R2 and V2 out of your observer positions and your line of sight vectors? So same setup as Gauss. And the basic premise is this. Here it is. There's a lot of, like, the devil's in the details, but here's the very basic premise. We're going to completely guess row 1 and row 3. And then we're going to solve Lambert's problem. right? So if you know row 1 and you know row 3, let me scroll back up to our picture here. Don't worry, I'm coming back. If you know row, then okay, observer position plus line of sight direction scaled by row gives you your position. So by guessing row 1 and row 3, you're really guessing your first position and your third position. And if you have a first position and a third position and a time between them, that sounds an awful lot like Lambert's problem. So we guess row 1, we guess row 3, we solve Lambert's problem, then we go backwards and estimate your position at the second time. And then further, you can solve the equation backwards and estimate your line of sight direction at the second time. This will be wrong. That makes sense. So you were saying, okay, if we were right about row 1 and row 3, then at this time, we would see the orbiting body along this line of sight direction. But you guessed, so of course you're going to get the wrong answer. But now what you can do is utilize techniques from optimization. And what we can basically do is iterate on row 1 and row 3 until U2 predicted equals or matches. I'm just going to say matches. This is never going to completely equal. Matches U2 measured. So those of you that have taken design optimization or something similar, you should be able to see that this is an optimization problem with two inputs, row 1 and row 3, and then, you know, all the other physics that's involved. But those are the unknowns. That would be like your design vector. And then the cost function would just be the angle between your predicted and your measured U2 line of sight directions. So actually going through and setting this up and coding this up and demonstrating that it works would be a fantastic final project for the class. So I definitely want to recommend that. But questions on Gooding's method? Otherwise, I think we'll take about a 10-minute break and then we'll reconvene and talk about Christian Hollenberg. All right, cool stuff. So it is, let's see, 12:43 for me. That would make it 2:43 for you. Let's say we'll take a break and we'll come back at 2:54. Welcome back, everybody. I hope we had a good break. Let's go through and talk about our next method of orbit determination. And this will pretty much wrap up our discussion on orbit determination. And this is the Christian-Hollenberg orbit determination. The Christian-Hollenberg method. So this feels weird for me to call it the Christian-Hollenberg method because I know the people who did this. Like I just think of this as that cool project that John and Courtney did a couple of years ago. This was developed at RPI, which I think is pretty neat. And it was done in the last 10 years. So this is just kind of to demonstrate that orbit determination is an ongoing field. There's still new ways of solving these types of problems. So what this is the velocity analog of Gibbs method. So with new measurement techniques and new sensors, it's not out of the question that we might actually have 3 velocities and want a position rather than 3 positions and want a velocity. So this is find R2 given V1, V2, and V3. And so we do this by fitting a circle to V1, V2, and V3. Now, I'll be very impressed if anybody can answer why we fit a circle to 3 velocities. Because with 3 positions, we fit an ellipse, right? We said, well, the orbit ellipse has a center at the center of the Earth, or has a focus at the center of the Earth, and it also connects these 3 positions. Now we're finding a circle. Anybody want to hazard a guess as to why?
Is it because all 3 velocities will be tangent to the circle? And I don't know.
No, I mean, thinking in terms of velocities being tangent, like you're kind of on the right track. I'm going to teach you something from orbital mechanics that you might have never learned before. It is called the orbital hodograph. So we're going to quickly dip back into orbital mechanics for a minute. So this was discovered by Hamilton in 1847. Hodograph is the curve traced out by the velocity vector of an orbiting body. You could think of it as an orbit expressed in velocity space rather than expressed in position space. So first it has this velocity, then it has this velocity, then it has this velocity. Now we live in position space, so this feels a little bit abstract to us, but it's a perfectly coherent mathematical construct, and it allows us to do some really cool things. So first, this is the subject of Richard Feynman's lost lecture. I get that mixed up with the book, The Last Lecture. Some of you might have heard about this. And it is also a 3 blue, 1 brown video. Highly recommend you go check that out. Here's the kicker. For any 2-body orbit, the hodograph is a circle. Not an ellipse, not a hyperbola, not a parabola. It's a circle all the time, which is extremely useful. That basically means, and this is what John and Courtney figured out, that velocity-based orbit determination can be boiled down into a really fancy circle fitting problem. which is really cool. I think that's awesome. So this turned into a great paper. Let me draw a quick picture here to make this make some sense. So let's say that this is your orbit ellipse. So this is in the parafocal reference frame. So here's P, here's Q, and let me draw some velocities here. So let's say that right here, this velocity, whoever it was that said tangent, yep, your velocity is generally going to be tangent to your orbit ellipse here. Now, I mean, not always, but here, you get the idea. There's going to be some velocity here. There's going to be maybe some velocity here. There's going to be maybe some velocity here. And some other velocity here. Notice that velocity 4, which is your apoapsis velocity, is smaller than velocity 1, your periapsis velocity, right? So I guess maybe I should have drawn this a little bit larger, but you get the idea. There's going to be some other velocity over here, call this V5, and some other velocity over here, called V6. And if you took these velocities and then plotted them all at the origin, something really cool would happen. You would get a circle. Now, it is not a circle centered at the origin. What you would find is that your periapsis velocity would be right here. And then you'd have some other velocity over here, call this V2. And then you'd have some other velocity over here, V3. And then maybe this is V4. And then this is V5. And then this is V6. Right? The velocities all trace out this circle, which is not necessarily centered at the origin. So what we can do is, here's P, here's Q, here is our orbital hodograph. We can, you know what, I'm going to try a little bit harder to draw a perfect circle. We can parameterize this hodograph using the, well, that's kind of a little bit worse. The vector, so maybe I'll use some other color here. Maybe use purple. Nah, purple's not going to show up well. Let's use blue. You could use this vector here from the origin to the center. We'll call that the C vector. And then its radius r. And if you know C and you know r, then you know everything you need to know about your hodograph. Okay. Now remember that a two-body orbit ellipse has these parameters. These are our orbit elements, right? You've got theta, E, A, omega, I, and omega. So what about the hodograph? Anyone want to hazard a guess? What's the full list of hodograph parameters? We know a lot of them already.
The vertical displacement of the origin. Or the vertical displacement of the center of the circle, I should say.
Yep, we're going to call that lowercase c. What else do we need to know?
Radius?
Yep, the radius r. Okay, what else? Well, notice this. The hodograph, apart from my own lousy drawing, is expressed as a circle that is aligned with the parafocal reference frame. So the hodograph is in the same frame as the orbit ellipse, right? So if we had the direction cosine matrix from the inertial frame to the parafocal frame, that would still be valid for the hodograph, right? So isn't that just these angles? These are still valid. And then also still valid is the angle theta for true anomaly. So I'll draw a picture in a minute. Theta, omega I, and omega are still valid for a hodograph. The new thing is C and R. Okay. So what that means is if we can establish, actually, I'm going to write this out. If we can establish a mapping that looks like E and A back and forth between C and R, then we can do IOD in velocity space. So then the procedure, and hopefully this is kind of starting to make some sense, right? If you've got three velocities, you can fit a circle to them. Somehow you can find your hodograph parameters. But then from there, if you know C and R, you can just cache those in for E and A, and now you've got your classic orbit elements, and then you're done, right? So let's make sure that this exists, this EA to CR relationship. And I'm just going to drop it in your lab rather than go through the whole derivation. Your periapsis velocity is C plus R. Your apoapsis velocity is R minus C. Your eccentricity is VP minus VA over VP plus VA, which is equal to C over R. Or you could say C is equal to RE. And then we can also say, separately from this, that C is equal to RE, which is equal to mu over H times E. So R is equal to mu over H, where H is that specific angular momentum, right? And it's reasonable to assume we could find the specific angular momentum. So if you know C and R, you can find E and, other way around. You can find H, and then we can establish a relationship between H and A. We can go back to the orbit, spaceflight mechanics review lecture. There was an equation in there, which I can't pull up right now. But if you know H and you know mu and you know a few other things, you can find A. So that would be kind of our relationship back and forth. Now let's talk a little bit about theta here. I want to draw you a picture really quickly. Or do we want to do that now, or do we want to do that at the end? I'm actually going to do that at the end. I think it makes more sense. I'm going to skip this for now. Stand by. Okay, so there's our hodograph discussion. What we're saying is you can express an orbit as a circle in velocity space. And now we can go into a little bit more detail. The circle will move, right? So if you have a more elliptical orbit, the circle will move further and further away from the center. And you'll reach a point where the circle just kisses the origin, and that would be a parabolic orbit. And then the circle actually moves all the way off the origin, and the origin is no longer contained in the circle for a hyperbolic orbit. I was going to draw a picture of that, but it's like, this is not a hodograph lecture. This is an IOD lecture. We can always go back and talk about the hodograph in more depth later. So back to velocity IOD. If we can fit a circle to three velocities, the circle parameters can be mapped to orbit elements. Okay, so let me draw a picture here. Imagine that you've just got, and this is in the inertial frame, so the International Celestial Reference Frame, or the ECI frame, X, Y. See, imagine that you've just got some velocity here. You can think of as a point in velocity space. And then you've got some other velocity here and some other velocity here, right? So maybe this will be V1, V2, V3. The first thing you could do is, and I'll use blue for this, you can fit a plane to those velocities. 3 points defines a plane, right? So fit a plane, and that plane will have some normal vector, which we'll call W hat. And you might say, Paul, didn't we use W hat for the vector that's normal to the orbit ellipse? It's like, yeah, we sure did. That's not a mistake. From here, we can fit a circle. So trying to remember where I drew those points. We'll say one here, and one here. The next thing we would do is fit a circle. And remember this W direction. So the next step, fit a circle. And then we're not quite done yet. There's one additional step, which is we need to define the orientation of the circle, right? So we basically are looking for the direction of the vector from the center to, or sorry, from the origin to the center of the circle. Okay. So imagine that this is our circle. And imagine that the center of the circle is right here. So this is C vector. Okay. Well, then C vector also points along the Q direction in parafocal frame, right? So then somewhere out here would be the P vector, and then up here is the W vector. And if you have P, Q, and W, now you have your parafocal reference frame. And we'll just say we define our orientation. And now we have a photograph. Okay. So now that we've seen it graphically, let's start throwing some equations at the problem here. Right. First, we want the plane normal vector W. And in this case, we see that W must be perpendicular to all of the velocities, right? So we can actually set up a set of equations that looks like this. Velocity 1 transpose, velocity 2 transpose, velocity 3 transpose. Stack those into a matrix, and then multiply that by W, you should get 0. Or we can call this matrix A. So we're going to say AW is equal to 0. This is what's called a null space problem. And it's related to a least squares problem. So maybe you've seen like AX equals B. In this case, it's AX equals 0. So what we're looking for is there's something about this matrix A where some inputs are mapped to 0 rather than mapped to something else. That's the way you could think of it. If A is a matrix operation, then this matrix collapses some things to 0. And what we're looking for is what vector in 3D space does A always map to 0? And in this case, the way we would solve this problem is using singular value decomposition. So we use singular value decomp. We'll say A is equal to U sigma V transpose, and then W hat is the column of V corresponding to the nearly 0 singular value. So what you'll find is that the singular values, which are basically a beefed up version of the eigenvalues, right? You're going to have an eigenvalue that's basically 0. You're going to say, well, here's a vector along which my matrix doesn't do anything. It just zeroes it out. And then just find that vector, and that's your W vector. Now, to be safe before we continue, we enforce the unity norm constraint. And the prograde assumption. So what does that mean? It means we assume that W has a norm of 1, and we also assume that the third element of W is positive, which is to say It's rotated, if we're orbiting the Earth in this case, you're orbiting in the same direction as the rotation of the Earth, not opposite the rotation of the Earth. That's a reasonable assumption for most spacecraft. I'd be very surprised if something was orbiting the other way. Okay, next, we introduce a temporary reference frame. And it's going to look like this. U, X, U, Y, and W. We don't really care where U, X, and U, Y are pointing as long as they're in the plane of the photograph. Later, we can figure out the P and the Q directions. We'll kind of come back to that later. But for now, we're going to say that U, X is equal to the first velocity crossed with the W vector. And then we're going to take that and normalize it. And then we're going to say that Uy is W crossed with X, right? And then from here, you could say that T inertial to whatever this temporary frame is Ux transpose, Uy transpose, W transpose. All right. Then we can project the inertial velocities into this frame. And because we're dropping the third axis, this becomes a 2D problem. So we can say for the velocity I, maybe I'll even write it this way. For the ith velocity, if we multiply this by T inertial to temp, and then we further multiply this by a partial identity matrix. So we're dropping the third column. Then this will get us xi dot and yi dot. So we're treating it as a 2D problem now. All right. If it's a 2D problem with an x velocity and a y velocity, and we have 3 of those, we're ready to set up the circle fitting problem. So we'll set up a linear system of equations to perform circle fitting. And that's going to look like this. 2 x1 dot, 2 y1 dot, and -1. And then this is a matrix. So 2x2 dot, 2y2 dot, -1, 2x3 dot, 2y3 dot, -1. And then this is what we're actually solving for. The center of the circle in x and y, and then some parameter g, which we'll figure out what g is later. This is equal to x1 dot squared plus y1 dot squared, x2 dot squared plus y2 dot squared, x3 dot squared plus y3 dot squared. Okay? So we solve the least squares problem, the ax equals b problem for photograph center. And g. So why do we care about g? I'll show you the equation for g. You know what? It's going to be easier to say it this way. G is just for now some nifty parameter. All right. And believe it or not, we're done. We can bring it in for a landing. Right? So here is R. R is equal to the square root of xc dot squared plus yc dot squared minus g. That's where g comes in handy. Now we have the radius of the photograph. We can also say that the c vector is just t going from the temp frame to the inertial frame of xc dot yc dot 0. So the center expressed in the plane of the orbit, taken from the temporary frame back to the inertial frame, gives us this c vector. Well, then we can say, okay, the scalar c is just the norm of the vector c, but the normalized c vector, remember c points along the q direction. So this is the vector c divided by c. Right? And then also p is just q crossed w. Right? And if we know p and we know q and we know w, then all of this gives us t from the inertial frame to the parafocal frame. Or that could also give us, if we want, omega I and omega. So we've got R, we've got C, we've got omega I, omega. We know that R and C can be used to find E and H, and then H can be used to find A. The last thing is our true anomaly. Now I'm going to go back and draw that diagram from before that I thought would be useful. And that is this. I think this is pretty cool. If you've got an orbit ellipse, which looks like this, and you've got a corresponding hodograph, which looks like this. That's meant to be a perfect circle. I'm doing my best. And here's the P direction. Here's the Q direction. Here's the Q direction. Here's the P direction. Here's what's neat. The position vector, maybe I'll use red. Use orange. There we go. The position vector is this vector right here, which has some angle theta associated with it. We know that at that instant in time, there's some velocity, right? And we also know, and we'll just define it this way, that this direction pointing along your position is what I'm going to call U parallel. Okay. Now, at that exact same moment in time, your velocity would be right here. It's the same velocity. We know that the hodograph center is right here. And then there's going to be some vector here from the center of the hodograph out to that velocity. And what's neat is that this direction we're going to call U perpendicular, which is exactly 90 degrees off from U parallel. Okay, why do I care about that? Well, because the angle between P and U parallel is theta. The angle between Q and U perpendicular is also theta. So that allows us to write some nifty equations here. The velocity in the parafocal frame is equal to negative r sine theta, that's in the P direction, and c, the scalar c, plus r cosine theta in the Q direction, and then nothing in the W direction, right? Okay, why do we care about this? Well, because we can take any one of those velocities that we started the problem with, and we can find the corresponding theta by first going from an inertial velocity to a parafocal velocity. So this is t inertial to parafocal times just one of those velocities, which we assume that the velocities at the start of the problem are in an inertial frame. Probably should have started with that. We get a parafocal velocity, and now we can say that theta is arctangent 2 of negative v parafocal 1 divided by v parafocal 2 minus the scalar c. And that's it. We can now go from 3 velocities to r, c, omega, I, omega, theta, and then also E and A if we so choose. And that is about it. I want to include some honorable mentions of other orbit determination techniques, and then we're done for today. But any questions on the Christian Hollenberg method of orbit determination?
Can the autograph circle have any horizontal shift at all, or is it designed to stick strictly be symmetric along the Q axis?
It's always going to be along the Q axis.
Okay.
Yep, good question. All right, so last is some IOD honorable mentions, because we could teach an entire course on orbit determination techniques, but I've decided to cap it at 2 lectures. Just want to expand your brain with like, these are some of the other problems that people have solved. So John and Courtney worked out the 3D analog to Gibbs method. The velocity analog to Gibbs method. So if you have 3 velocities, find a corresponding position to one of them. Or in this case, we're just going straight for the orbit elements, but you see how that's the same thing. They also worked out, what if you have 2 velocities and some time between them? So that would be the velocity analog of Lambert's problem. There's also, if you have bearing and range rate of spacecraft with respect to central body, like the Earth. So if you're measuring the Earth's bearing vector and its range rate with respect to you, you can get your, you can find your orbit. There's also a set of inertial range rate measurements. So thinking about measuring the Doppler shift of starlight, right? Or something called stellar aberration. If you measure stars, you can get a component of your velocity. And if you get enough of those components of your velocity over time, you can fit in orbits in them. I did that. That was part of my dissertation. The next one is heading information only. So heading is the velocity direction. Like, which way are you heading? So you know how speed is the norm of velocity, heading is the direction of velocity. So if you know that you're heading in one direction, and then later you're heading in a different direction, if you have enough of those heading measurements, you can do orbit determination from that. This is useful, say, if you're tracking features on the surface of the moon and you're in orbit, and you do what's called visual odometry. You can determine the direction that you've moved between the 2 images, but not necessarily the distance. You get like a scaling problem. And you say, okay, well then just forget the scaling, just give me the heading, and you get enough of those headings, and you can do basically a batch estimation of your orbit. I think this one and several of these are less than 10 years old. So these are definitely new. And then of course, there's a whole body of stuff that we didn't really talk about, which is using radio frequency measurements. Oh, I can't talk today. Sorry, I'm getting tired. Using radio frequency measurements. So this would be, distance. There's time, distance of arrival of signals, and there's also frequency difference of arrival. Basically, most of what we've been talking about are given positions, given velocities, given things that you can get out of a camera, which is closer to kind of my area of expertise. I don't know nearly as much about radio frequency measurements. But any of these would be a fantastic final project idea, is to kind of dig into one of these deeper. So I wanted to put those in your head. And that's about it. That's everything I have for today's lecture. I think we're good to go, right? Let's see here. Oh, this is embarrassing. This is lecture 8. Sorry about that. I think I missed count somewhere along the line. This should say lecture 8.
Yeah, I saw that at the beginning, and I'm like, I know
Oops.
I didn't watch the last lecture. I'm pretty sure
No.
that was lecture 7, but I wasn't there.
Yeah, no, definitely. I screwed up my bookkeeping. This is lecture 8, and I'll need to put like a little thing in the video about that because, like, oops, I said lecture 7. Cool. All right. I was like, something definitely felt fishy about that. I'm glad I went back and checked. This is lecture 8. And then Wednesday will be lecture 9, and we're going to talk about matrix vector calculus, which is going to be really fun. Any other orbit determination questions, or are we good for now?
I think the problem is because I missed 7 and I was still catching up from the ones I missed from a couple of weeks ago. I feel like I was rushing to actually manage to write everything down, let alone actually absorb the information. So I think I'm probably going to have to either watch through this again or do some reading tomorrow or tonight.
Sounds good. And really, the big one that you'll need for the homework assignment is Gibbs method, which is the first one that we go over and the simplest one that we go over. So if you're feeling a bit overwhelmed by all this, like, not to worry, it's not quite as bad as it looks. Okay, good stuff. I'm going to stop the recording, but I'll stick around, especially if anybody has any homework questions. But yeah, thanks everybody.